Hey, this is Mr. Mitchell with a video about the periodic table, and let's go ahead and get to it. Periodic table groups similar elements together, and we've talked a little bit about it. There's a guy in the bottom left-hand corner here whose name is Mendeleev. He's the first one to kind of put together the periodic table. Now, he put it together according to atomic mass, which is this number down at the bottom here. But today, most people put it together, or scientists put it together, according to atomic number. But Mendeleev was on the right track, and what he did was just invaluable toward getting this, I guess you'd call it a document. But anyway, let me talk about different parts of the periodic table. There are periods which are horizontal rows. For example, this is a period. This is a period. This is a period. These are the horizontal rows. They are by number of protons, and as you go through them, the number of protons increases by 1 as you go along the period. Orbitals can also be determined by periods. You know, you have this is the s orbital, this is p orbital, and so on and so on. There's also something called groups. Now, where periods were horizontal, groups were not. Groups were vertical. So all these are different groups, and you can see we have names for these groups, which we'll talk about. Sometimes groups are called families. Let's talk about atomic number. Atomic number is number of protons, and you can see the number of protons right here on the periodic table. So for rubidium, the number of protons is 37. The atomic mass is the number of protons plus the number of neutrons. And you can find that at the bottom of each one. For rubidium, I don't know if you can see it from your tablet or whatever you're looking at, it says the atomic mass is 85.47. Now, you can't have 0.47 neutrons to add to this 37, but that's an average. You'll find later on that you can have the average, you'll have to average together the number of neutrons at times. But anyway, long story short, atomic mass is down here at the bottom. That's protons plus neutrons. Let's talk about ways to classify elements. We have metals and nonmetals. On the periodic table, most of them are going to be metals. There's kind of a dividing line right about here between metals and nonmetals. To the left of this line is going to be metals. To the right of this line are going to be nonmetals. Now there is an exception. Hydrogen here is a nonmetal, but you'll see later, or it is put over on this side because of its valence number. So nonmetals to the right, metals to the left. We have something called semiconductors, and sure enough, I misspelled it right here. Sorry about that. But all these elements that are just right along the edge here of this borderline, they kind of take qualities of metals and nonmetals. These metals over here are going to be conductors. They conduct electricity, where nonmetals don't, but these can conduct at certain times, and they're kind of softer than most metals would be anyway. So those are semiconductors. These are also called metalloids. We have the alkali metal group, which is straight up and down through here. This whole group 1 is alkali metals. You may remember their valence is going to be +1. We have the alkaline earth metals, which are all up and down this group. Their valence is going to be +2. Now, we have these two are very reactive. The alkali metals are even more reactive than the alkaline earth metals. Alkali metals are soft and shiny, and they react violently with water. They're very reactive. Since they just have that one valence electron, it is easily removed. That electron wants to fly away, you will find out. So as a result, you very rarely, if any time, find them in nature at all, because they're going to have that electron that has flown away, and they'll actually be an ion or a compound. Now these alkaline earth metals are a little less reactive, but they're still, overall, they want to have those two two electrons fly out, and they will become ions and compounds pretty easily as well. Now that's not going to be the case. No, sorry.
Mr. Tomlin, please come to the office.
That's not going to be the case for these transition metals. All in pink here are transition metals. Now they don't do a whole lot of reacting. They just don't have the right valence to do a whole lot of reacting, and they very rarely will you find them as ions. Oh, it happens, and you will occasionally find some compounds, but that just doesn't happen as often. Now, there are two periods down at the bottom here. These last two periods are placed at the bottom so similar elements can be grouped together. These last two, you may notice this starts with 58. So this whole section right here would actually go after lanthanum right here. But just for the ease of the putting things together is why these two are lumped down here. They are still metals and considered transition metals. So we have, let's talk about all these nonmetals over here. Pardon me. We have the halogens, which is group 17. That's up and down through here. These halogens, you know, they're going to be highly reactive also because their valence is going to be 7. And here's how you can remember the valence number. You've got 1, 2, this 13 is 3, 14 is 4, 15 is 5, and so on. So this group 17 has 7 valence electrons. It is really wanting to get that last electron. So they're very receptive to making, to becoming ions and to becoming compounds. Now that's not going to be the case with these noble gases here. Noble gases, you may remember when we talked about valence electrons, had all their outer shell filled. So they do not want to react with any of the other elements. They do not, you just do not find them in ions, you do not find them in compounds. Their orbitals are full. And one thing I forgot to tell you about semiconductors is that the most common semiconductor is going to be silicon. Let's talk a little bit about ions. If an electron's outermost energy level is not filled, they may become an ion. And we mentioned that this whole row of alkali metals wants to let go of that one extra element or one extra electron. We have like hydrogen, which has that one electron right there. And since it has just one, it doesn't like for it to have just one. It wants to be let that electron fly away. Now when that electron flies away, it loses the charge of the electron. All the electrons have a charge of -1. So what's left in the hydrogen is just that one positive that is inside the nucleus in the proton. So if you have a hydrogen ion, you would put it as hydrogen and you'd put plus here. So every one of these alkali metals, whenever it has an ion, an electron fly away, it would have a positive charge, and that would be called a cation. A cation is an ion with a positive charge. Now here in group 17, all these halogens, they are just dying to get electrons from all these alkali metals is where they get them mostly. So whenever you have, let's say, fluoride accepts an electron, that means it's going to have more negative charges than it had before. So if it accepts an electron from another element, it's going to have more negative than positive, so you'd write it like this, and it has a negative charge. It would be an ion of fluorine. So that's kind of the basic gist of what an ion is. An anion is going to be one of these negatively charged ions. And here's how I remember it. A negative ion is how I remember it. Anion, a negative ion. Does that make sense? Okay, let's talk a little bit about something else. We have something called an isotope. Now, an isotope doesn't have to do with the electrons. An isotope has to do with the neutrons. Now, if you have an isotope, you have a different number of neutrons than normal. For example, here in carbon, you can tell the number of neutrons by taking 12 and subtracting 6. You have the atomic mass, and you subtract the atomic number, which is 6. But you notice that it's not an even number. You can't have 0.011 neutrons left in there. This is an average of the number of neutrons, which tells you that sometimes there are more than 6 neutrons. And a good example is hydrogen. Here we have 3 isotopes of hydrogen. You can see exactly what we have here. This is what hydrogen normally looks like. You have the proton, you have the electron, but every once in a while you'll have a neutron that has come in. And every once in a while you'll have 2 neutrons that come in. So you actually have 3 different isotopes of hydrogen. This one right here is what it normally is, but the other 2 happen in nature some. And you can see from the atomic mass here that it does happen some. There you have an increase in the mass. Now what happens to the mass of this one, which is labeled as deuterium? The mass is going to be higher than 1. In fact, they have labeled it as the mass is going to be 2, and they've labeled it here as the mass is going to be 3. So that since the weights of subatomic particles are so small, the average atomic mass will be something called an atomic mass unit. This is in atomic mass units. It doesn't really have a gram beside it, but it can. And here's how you can convert it.